Okay, so with the Photron CRYSTA, the high-speed system, we have a conventional high-speed camera, and once again we have this photonic crystal affixed directly onto the CMOS sensor. So we get a normal camera with all the normal connections, the in and out, so that we're able to synchronize it very precisely to anything else. We can trigger it remotely. We have all the usual abilities to trigger the camera either in start, end or center mode. And we have a conventional Nikon F-mount on this one at the moment, but we can replace this just as easily with a C-mount so that we could affix that directly to your microscope. The only other difference is that we put a bandpass filter, a 520 nanometer bandpass filter on the front of the lens here. Other than that, a typical test setup is back illumination with a LED light source. Obviously very important it's flicker free as with any high-speed video. And we have 520 nanometer sensitivity, a circular polarizer on the front, and then when we squeeze our acrylic test piece here, we can have results such as we see here. So again, you can see very clearly the stress actually being induced, and what we did is we took a simple line across the test subject, and we can see that in what we call our time-space chart, and then also we can actually get some values in nanometers across the retardation across our test sample there. So that's the CRYSTA, the high-speed side. We also have another system which I'd like to show you now. Okay, so with the WPA Kamakiri system that we're showing here, we have very much a similar setup in the sense that we have our light source with a circular polarizer, although this actually uses a quarter wave plate, so not so important there. And in this case, we have a filter wheel here that we're able to take an image, we rotate the filter at 3 different wavelengths to capture our images. So I've already calibrated the system. What I'm going to do now is get my glasses in the shot. And as you can hear, possibly, you can hear the filter wheel operating. And over a period of time, we'll build up 3 images to get a very accurate view of the retardation that's left in my very cheap reading glasses from the actual manufacturing process. Okay, so now we can see on the display here, we have a view showing my glasses, and if I adjust the scale, in this case from 0 down to about 200, we can actually see the way that the stress is distributed inside the sample, and we have a very detailed ability to generate reports on this based on both the polarization, and we can also show the axis. So here we can actually see the way that the stress is actually being distributed inside of the material we're looking at. So this can be very useful for scientists and engineers alike to understand how the stress is induced and also the direction it's going to go. Some directions may not obviously affect the performance of the product, where others may be very critical to it. So basically we offer a wide range of systems. We have these systems available in our office in San Diego, so if you have any interest in understanding the polarization and the retardation of your transparent or semi-transparent materials, and we can operate with any materials as long as a minimum of 30% light is transmitted through the material or fluid to enable you to better understand what you have. Andrew Bridges signing off from Photonics West 2019. Thank you for your time and interest.